And I find this recording is so useful because when I prepare this, I definitely don't remember what the notes was about like last year, and then I just rewatch my own video. Then I understand what's going on, and it's so much easier. And actually, it works very well that way, like for you guys also. I really suggest it because nowadays technology is so simple. It's easy to make your own notes in video, and then it much clearer after you explain to yourself like what's going on, and then and afterward, like for me, it's like my memory is like at most 1 month. After 1 month, I definitely forget anything about that subject, but I can go back and rewatch the video, and I can like quickly understand what's going on again. So it's really very helpful. So we talk about dropout and also like some other regularization, like data augmentation and so on. So I guess we stop somewhere here. It's basically saying like you can think of regularization. It's just trying to make model less extreme, and one paradigm of doing regularization will be introduce some randomness to the model. So either in dropout case will be like randomly removing nodes, or like if for job connect, this one we didn't really go through in detail, but we'll be randomly dropping like connection and so on. Or like even you think of data augmentation, it can be like randomly generating, for example, you have images randomly resized with different scale, or like a little bit rotating in different angles. And all this randomization can if as you train the model this way, it kind of seems like your parameters is trying to average over all these possible models, trained models. So therefore it will be less extreme, therefore you can think of this as regularization. And so today we'll talk about automation. Actually we'll kind of, I guess the entire class will talk about optimization. So basically this is not difficult optimization. It's not like some nonlinear or like convex optimization class that have more complicated math, because all of them are based on like rather simple intuition of doing steepest descent. You find the slope and just going down there. So we already mentioned some of them, some variation, and of course the vanilla steepest descent has one issue. It will be something like if you have your kind of the objective function is kind of scale in one dimension, or like you can like this one, like in one axis is like kind of the slope is much less steep than the other slope. And then if just go downhill like with let's say this vanilla like naive steepest descent will just kind of oscillating and will not be very efficient, because here the steepest slope is this way, right? Steepest gradient is this way, or steepest downhill will be this way, and when you're here, steepest downhill this way, and so on, back and forth. So we already mentioned that one possibility. Actually, before that, like, let's talk about that. So one possibility is like we're trying to kind of like initialize some momentum. So basically, the momentum will be like, instead of using this is the original gradient. Instead of like using the original gradient directly to update your current location, you just update it with a kind of moving average of that gradient. So you look at this guy is basically a moving average, right? You have dx here, you have the v is basically, I mean, like this kind of moving average, right? So instead of like using y, you're basically is like updating using this s, and s is basically a weighted sum of your previous s with the current estimate of the y. if you elaborate that, you will see that ST in terms of Y will be like this. Will be basically will be weighted much heavier for the reason Y, and then for the as time goes, farther and farther past, then we'll have a much smaller weight. So it's like an exponential moving average. So another remark I'd like to point out is for optimization, in particular high dimensional optimization, we always most of the time when we do simple low dimension several parameters optimization, we often worry about whether we settle into local optimum or really the global optimum. Right? We would like to go into the global optimum, but maybe we are stuck in local optimum. And of course, if you're stuck there because the gradient is equal to 0, you just simply cannot get out, right? Other possibility you won't be able to get out is in a saddle point also. So here also your the gradient will be 0 there, so therefore you cannot go anywhere. But actually, come to think of that, what do you think is more common, local minimum or saddle point? Which one is more likely to occur? Which will be? Yes, intuitively it looks like so, right? But our intuition is not correct. It's only on low dimension. Just think of that. If we are really in high dimensions, let's say just 10 dimensions, the probability to be local minimum, you need to be settled somewhere. In each direction you go, you are the minimum, right? But in saddle point, it's basically saying that you go one of the way, it's actually not every point is minimum. Some of the way actually you will get out of that, right? Apparently, it's more in high dimensions. The possibility that in any direction is a minimum is actually quite low. Actually, local minimum in really high dimension is not really that likely. But on the other hand, it's the saddle point is actually quite likely because you come to think of that, only one of the some of them is this way. What I want to say, in one of the direction, not just minimum, but also may go down. In some of the direction, it's really minimum. This possibility is more likely, right? Does it make sense to you? Yes. Does it make sense to you? I don't know. Sorry, what's your name?
Robert.
Robert, yeah, but in front of Robert?
Patrick.
Patrick, okay. Oh, I try to remember two names this time. This week. So, yeah. Patrick, I agree with that because I don't think I articulate very well, but you think of that, if you really have a local minimum, each of the direction have the same characteristic, right? But if you have a saddle point, some direction you can have this way, some direction can have this way. It should be more likely, right? So it seems, yeah, so but anyway, it's just some interesting facts to think of when you get into high dimensions. And also another point is unlike really some optimization problem, remember that for what we are dealing with in machine learning is not completely an optimization problem because your objective function is just an estimate, right? It's an estimate that given your data like that, and given the limited amount of data, it's like that we are trying to minimize the training error, right? So therefore, the real objective function can be different. And sometimes you may not even want to get into the local minimum if the local minimum is very steep. Because this very steep local minimum can be just some minimum due to overfitting. Because if you have like more training data, like oftentimes when you have something like that, like very kind of irregular, very steep terrain here, it's likely will be smoothened out when you have more data that come in. And this may be just simply gone. So even maybe this is the global minimum, but this may not be the global minimum you really want to fall into. So, but anyway, like, okay, this is interesting to think of, but in practice, it's actually hard to utilize this kind of like inclusion. So, but let's go back to the momentum thing. So we mentioned that the simplest modification for the vanilla gradient descent will be simply add the momentum there, right? So if I add the momentum, actually I like to call it inertia. It makes more sense, right? It's basically like you are not trying to change your direction easily. So then you will be something like that. You kind of like oscillate less seriously and eventually get to the optimum here. Now let's talk about one additional modification about momentum. That is something introduced, I forgot, in the 80s or something, like, but people pull it back. Like, this is of course like from optimization research, but people pull the result out like using machine learning as well. It's called lateral accelerated gradient, something like that. So the idea is something like this. So if you are trying to, let's say, introduce some momentum, right? So some regular momentum, then you have a situation like this, like you are moving here, moving down, moving down, moving down. Your gradient is getting smaller, so you can see here the gradient is actually shrinking because you're accumulating the gradient. Gradient is shrinking, but you overshoot a bit. Now the gradient is moving backward, accumulate backward. But wait a sec. No, actually not yet, because you have the momentum there, right? As you say, like you have the momentum there, you overshoot, right? Here, without the momentum, you should go back. But now with the momentum, you overshoot, so you will continue to go this way, and you still have the momentum go this way. Now finally going back, like something like that. So the argument of like lateral accelerated gradient is that like the simple momentum update sometimes will lead to overshooting. So what he suggested is that like instead of computing utilize the gradient here, what it means is, for example, like here, next time I update, I move to here, then I compute the gradient here and try to update this accumulated gradient and move back, and I use this current gradient to compute the accumulated gradient, right? So what he suggests instead is we'll just look ahead. So here we'll already first, for example, at this step here, if I compute the direction for the next step, I'll utilize the gradient at this point, right? But instead using the gradient at this point, I'll first look ahead. I first move the ball already to here, and then I compute the gradient here and use that gradient to accumulate to modify the accumulated gradient. So that will be something like this. So the original momentum update will be like I'm here, I compute the gradient, and I have the previous accumulated gradient, the momentum. I added them together. I have the actual gradient is here. I mean, actual direction to move is here. And for this one, I will first look ahead. I used my previous momentum to move up to here. Now I add here, I compute the gradient. And then I added that to my momentum step. I mean, the gradient from the momentum, or like the accumulated gradient. And therefore, the actual step will be like this one instead. So, clear? So and so therefore will be like an equation will be simply like this, right? So instead of using the gradient at the current point, we'll just move ahead. So we added this one and compare the gradient. So in terms of implementation, it will be a little bit troubling though, because we like to deal with just the gradient at this point and also the value at this point, because I remember when we do backpop and so on, we always compute the local gradient, right? At this point we compute the gradient. So if we need to now move ahead to compute the gradient, we need to do some modification. It's kind of complicated. So, but it can be fixed by doing some rename some variables. Let me just call it x tutor, like this guy here. X tutor t is xt plus mu vt here. So then if I substitute that, then I have this form is like what we want. And x tutor t then is equal to this guy, right? Is equal to this guy. I just copy it. But xt is updated by this guy here, so I have this substitute into here. So and this again, like xt minus 1 is equal to x tutor t minus 1 minus mu vt minus 1, right? So I have this one here. So then rearranging the terms, I have this. So basically, so then I can update x tutor t instead, and also like compute the gradient at that point. And this is kind of the result for the last law of accelerated gradient. So for this simple case here, it's quite good. So as you can see, for this optimization problem, like energy is actually really quite good. But there's a catch here also. Like a further catch is that if your sample size is small, so if you have basically a problem with limited amount of training data, sometimes this energy won't be very good. As some people pointed out, I didn't have that one included here. So, but anyway, like for this one, energy, it tends to be like if you have more uncertainty with your optimization objective function, the acceleration effect will be smaller. So let's talk about like another possible update. So something known as ADGRAD is by some fellows in Stanford like several years ago. So it's something they did something actually quite simple. What he does is this is the original update, right, without this guy here. So now with this one, this cache here is simply the accumulated square of gradient of the accumulated square gradient of the previous how should I say accumulated the previous square gradients. So and then he just kind of normalized by that one. So if you look at that, the effect it will be simply you want to kind of like at the beginning your gradients you can let me put it this way. You can think of this as like just a automatic adjustment of your learning rate or like your iteration step, right? So basically, as times go by, automatically you reduce your step like more and more. So it seems to kind of make sense if you think of like you in general you tend to, as you go near to the optimum value, you expect that you want to reduce your step, right? Just try to minimize the probability of overshooting. And that's what they did. This is another kind of like, this is adequate. So you see like the step is just like reduced quite a bit, like as your number of step increases because of this normalizing step, at the denominator. Now there's another one called RMS Pop, is by Jeffrey Hinton, so it's actually quite similar to adequate. So the only thing is, what they do is that instead of kind of normalize it, or like normalize it by the square of simply sum over the all the square gradient. So instead, like they will use the running average instead. So this, remember, this is simply running average, right? So they will just use a running average and normalize with a running average. And this is kind of interesting because this work was never published, and it was only mentioned like in his Jeffrey Hinton's Coursera course, like given in 2012. So therefore, like people cited this result, like cited this method, like based on the Coursera course, really. So it's very uncommon like this way. This is another, like it's based on like RMS Pop, like it looks pretty smooth for this particular small example. And finally, like we have something known as Atom. This is probably one of the most popular one. Basically, it's like combining several of the previous idea. So it do the normalization, that we have a normalization of the square gradient. Again, this is just, they also use a moving average approximation for that, and moving average as moving for that. And also, let's see. Wait a sec. Yeah. Also, like Also, they have a momentum step also here, right? This is simply a momentum step. So we have a moving average of your gradient. So M is a moving average of gradient. So he take into account both ideas. You have a momentum, so it's a basically moving average of your gradient, and you also normalize with the square gradient, or the norm of the gradient, that is also like is smoothed by a moving average as well. And practical implementation, it does have a little bit small bias correction, because when for the, let's see, yes, because we are using moving average, right? Initially, this beta 1 and beta 2 will be equal to 0. So, and to take into account like this initial problem, we simply, like for the first, we add this new term here. So as you see, like when for the first couple steps, when t is equal to 1, right? T equal to 1, this is equal to 0, and then like this is equal to 1. So therefore, like if I substitute this first moment into here, then basically substitute this guy into here, this part got cancelled with the denominator, right? So it's just get back dx here. And similarly for this guy, I just get back dx square, something like. So it's just I added this additional bias to take care of the first several steps. But as your t get bigger, then this guy will just diminish, right? So it will be just the same as what we have earlier. So that's basically Atom. And this is really amazing, because last year I checked it, I had 6,000 citations. I mean, it's like 2015 paper, and And it's a very simple idea as well. There you go. So if you're really interested to do really research have impact, this is a very nice idea. But I guess I probably very competitive as well. And this is also like an example like for Atom. It turns out like Atom is just currently probably the most popular one. And this line I'm showing like, now we talk about these optimizers, right? Different optimizers. Let's just stick with Atom. Still, we need to think about what kind of learning weight we're going to use, right? So learning weight is also a problem. So apparently, if your learning weight is set too high, you will just have exploding of your loss. If you're setting too low, let's see, then you will take very long time to converge. Or like when you take like not too, not very high but still high, you may converge quickly, but then you can't settle because like then you are near the optimum there, but you keep overshooting like near the optimum, so never settle to the real optimum there. So therefore, you may have like a high kind of loss like at the end. So the best will be somewhere like this, right? But of course, this will be tricky to accomplish. So there's lots of kind of tiny control about this learning rate that you can tune really. So some people try is like to do a learning rate decay. So basically, different kind of decay. You can do a step decay, like every once in a while you just decrease the weight like by half, or you can have like exponential decay simply with a formula like this, or like 1/t decay. So there's lots of possibility you can do. Like for example, this is like doing a kind of step decay. So you have start with like pretty high learning rate, then you kind of settle. You don't know, you settle here. So then settle here. You imagine probably it's like overshooting, right? You are near the optimum, but you are kind of keep on overshooting like that. Let's say this is the optimum, but you just like that. So then at this time, then you may decrease the learning rate, right? If you decrease a little bit, now you're somewhere like that maybe. Then you see there's a drop here. Here. Now maybe you can try to still decrease the learning rate further, then you can get even smaller loss. And that's about learning rate. Now let's talk about this. The method we just talked about is a first order method. It's simple, just based on the gradient, you look for the steepest descent and so on. One of the issue of those problems is the learning rate. Right? If you look at the earlier what we have, we need to figure out what are the learning rates there. And another possible approach is look into second order approximation. So what do we mean by second order? Is that like we approximate. When you think of like steepest descent, you're essentially just approximating, for example, like in 1D would be something like I have whatever some at this point here and want to look for this optimum here. First order, we will just look into the current slope way and then go down with like certain step. I just draw too much. Maybe go down that much to here, and then like here, based on this slope again, I will see like how far I should go down and so on and so forth. So for the second order, I will not only take advantage the slope, I will take advantage the curvature as well. So then, in a sense, it will be like I will approximate locally what this is like as a quadratic function. So for example, like I will approximate this based on like this local information that I can fit into a quadratic function here. Then since I have a quadratic function, I immediately know that what's the optimum, right? Where's the optimum is simply here. So then I can immediately say, okay, optimum is here, so I start at this point here again. Now, I'm trying to fit this with a quadratic function. And now I will say the optimum is here, so I will move to here. So this potentially, like, you can get down to the optimum much quicker, like with much fewer iterations. But of course, it increases complexity. So in high dimensions, basically you will need not just a gradient, but also need to have some hashing matrix here. Basically, if this is an n-dimensional space here, then this hashing matrix will be n by n, basically. And so have this with this guy, let's say if with the current point here, theta here, we approximate this j theta with this one here. Now if we're trying to find the optimum, find the minimum, then simply I should just take the gradient, take the gradient of this guy and set it to 0, right? So take the gradient of this guy with respect to theta, then the first term is basically is a constant, I can ignore that, and take the gradient with respect to this one. This is just does not depend on theta, right? So therefore, like I should just get back the gradient j theta naught here. And for this guy, if I take gradient with respect to theta, I think we did it previously. This, I don't know whether in this class or like course or like the other course, but what we get should get something like H transpose plus H times theta minus theta naught. And of course I have 1/2 here, right? So I should have this add together is equal to 0, therefore. And because the hashing matrix in general is symmetric, so this actually is just equal to H here. So H transpose is equal to H. So therefore H transpose plus H over 2 is just H. So then you rearrange the term, you get this theta is just equal to theta naught minus, so I have, okay. I have, let me write it like this. Gradient j theta naught plus h theta minus theta naught is equal to 0. So I multiply h inverse everywhere. So I have h inverse here. H inverse multiplied by h got cancel. So I have theta is equal to theta naught minus h inverse j theta naught. So exactly this guy here. So, and again, the nice thing is that we don't actually have a learning rate here, right? So we basically just as long as we know the gradient and we know the hashing, then we know exactly where is the optimum there, assuming the current quadratic approximation. But there's no free lunch here. The problem is that like the gradient is inexpensive, but the hashing is actually very expensive because gradient is only n by 1, right? Only have like n scalar values there. This is basically n by n. And what's more, you need to take an inverse of this hashing, and this will be like n cube, kind of big O n cube, something like complexity. So that means that like if you have 100, like let's say 1,000,000 parameters, then you are talking about 1,000,000 cube kind of computations. This definitely is too much. So therefore, like this brute force one is rarely used besides like a really small like toy problem. So in practice, we always use something known as some quasi-Newton methods that basically we are trying to, instead of brute force computing this inverse Hessian, we are simply trying to do some lower order approximation. For example, have some rank 1 approximation, and rank 2 approximation. Rank 1 approximation is simple but not too commonly used. Rank 2 is much more popular. The most popular one is known as this BFGS, that we will explain a little bit later, and also something also known as DFP, and some other method known as DFS. And even for BFGS, the computation intensity is good, but the problem is that you still need to store the entire inverse hashing. So the inverse hashing is n squared. So if you have 1 meg per parameters, then you have what, 1 terabyte of data. So that is not very realistic, even for, at least it's not realistic for a home server or something. So then we have this LBFGS will be a trade-off. Instead of like storing the entire inverse hashing, we are trying to trade off space with time. So we use some more computational steps. And okay, actually I will talk about more later, so you will see about that. I got this is a reference when I prepared this class. I didn't look at the reference this time. I just relook what I talked about last year. So this is a very good video. If you guys can understand my accent or like understand everything, like this is a video worth. But he has a different accent also. He's Russian, I believe. So, but his accent probably is more understandable than I do. So there's also find some lecture notes from here. And this lecture notes point out some book here. Like it looks pretty good. But there's some problem is that I don't like is he used a weird notation. Kind of they use B to stand for hashing and like H as inverse hashing. So it doesn't seem to be a very common notation. So but anyway, as just continue what we talk about. As we said, like we'll instead of like compute the hashing by brute force or like the inverse hashing by brute force, we'll kind of like approximate that. And let's call like the inverse hashing as B. So maybe I should put a K here also, like HK inverse. And then like, so therefore like, if you remember earlier, we have the iterative step is like that, right? So therefore the direction to go is basically this is equal to H inverse times the gradient, right? This gradient here. Is the direction is to go is basically this way. Inverse hashing times the gradient. And so in the original approximation, we can just simply compute this to get the optimum, right? This should get us the approximate optimum. But because our hashing is an approximation, we can gain a bit like by using line search. We just like look into that direction, then we also like want to look at like what's the along that direction, which point will be exactly the minimum. Then afterward we just update the gradient and then reiterate and so on. So that's the general framework here. Any questions? Hopefully not yet, because we will get into more details. And really stop me because this can get a little bit confusing. But as I mentioned, this kind of stuff is really good to learn it in school, like in a lecture form, rather than like trying to grind it yourself like through books, because it's quite painful to read math book. To be honest, really. If you guys have the did that before. My reading rate of math book on average is half an hour per page. So I mean, like, so it's yeah. Oh, of course, the introduction is different, right? The introduction, was about maybe like 10 minutes per page or something. But then afterwards is, it's really, really painful. So and also this stuff is quite it's not really hard to understand. So please just stop me like if you have any question. So again, what we have is basically we have the gradient can be, how do I write that? Oh, okay. Think of the Hessian is the second order derivative of the gradient, right? So therefore, like, it's the what did I say? Hessian is the derivative of the gradient, right? So therefore, like, Hessian should be something like gradient j, let me just say j k plus 1 minus gradient j k over theta k plus 1 minus theta k, right? Something like that, right? So if I rearrange the term, then I should have this, right? Okay, so because that's the definition of derivative, right? If you take a derivative of something, let's say fx, the derivative of that is approximately fx plus delta x, maybe let's say, minus fx over x plus delta x minus x, something like that, right? So, and this is basically saying h is the derivative of delta j, right? So therefore, I will have this approximation here. Of course, this approximation will be exact if this goes to 0, right? So typically, this is equality. If the limit that basically this delta x goes to 0, or like this part goes to 0. So, but anyway, we can write this approximation assuming like theta k plus 1 and theta k is not far away. Now then, like, we can write this difference. I call it pk, and I move this guy on the from left hand side to right hand side. Oh, sorry, right hand side to left hand side, and call it like qk. Then this I can rewrite as a hpk is approximately qk, right? And I will just make it exact. I will just claim it's exactly equal, and this is known as secant equation. I will just make it exact. Now let's say I want to have a rank 1 update. So we're trying to make a rank 1 update of our Hessian, right? So rank 1 update will be a rank 1 matrix, right? So you have a column vector multiplied by a row vector. It give us a rank 1 matrix here. And this basically specifies any kind of rank 1 matrix, right? Any kind of rank 1 matrix can be represented by this. So then let's try to make an update like this. Then I have this one. So now I want to satisfy this secant equation, right? So I multiply that pk is equal to qk. So rearrange the term. I get this here. And further rearranging the term, I get this here. So note that I need to be very careful when I move stuff around. I can move this down here. It's because this is a scalar. So it's not like I can move things around like arbitrarily. Like for example, I cannot just move hk down and like over hk, something like that, because hk is a matrix. I cannot just over that. It doesn't make any sense. So I can move this down just because this is a scalar. And now there's some freedom here, right? I can pick whatever v I like. I have an update for u here. I say like u given v, u will be like this, but I didn't specify v yet. But since I have an additional constraint, right, I know Hessian has to be symmetric, so let's force h to be symmetric. Then in this case, if I pick V as this guy here, then as you can see, I pick this as V here. Then my H will be, okay, H is where? Let me go down here. H, okay, H is here, I'm sorry. H is here, yeah, H is here. So if I pick U, pick this as V here, then I will just have okay, let me step back again, like so, because I'm sure I may get you lost, because it even get me lost. So I have, this is my update here, and now I substitute this guy back to this one here, right? So therefore I have something like this QK minus HKPK times V transpose. That's my original update here, is something like this. But now I'm saying that I need to have the update afterward is still symmetric. So what I did is simply assuming this guy is equal to V, something like proportional to V. So then I will be symmetric, right? Or like this is equal to V, so this will be symmetric. So therefore, like the whole thing become this one here, become this, and where V is just equal to this guy here. And this is the Vancouver update for HK. And of course, I remember that like we actually not interested in H. Actually, we are interested in really B, that basically H inverse. So, but it's okay. We don't need to rederive everything here, because we know that like since we have like HP is equal to QK, right? So, and therefore we will have like H inverse QK is equal to PK, and H inverse here is just B, right? So we have PK is equal to BQK, and for this one we have derived this guy here, right? So therefore, like simply we have this condition, then we should have this expression here. And this is basically our rank 1 update. But actually, this is not BFGS yet. This is the BFGS, I would say. BFGS is a rank 2 approximation, but basically it's a very similar idea. So if you have a rank 2 approximation, the simplest case would be simply like this, right? We just add an additional term here. So we'll consider a update with a not just this U transpose, but we also add a this W transpose. So then now in this case, this will give us a rank 2 update here. Then of course we need to decide what do we pick like UW and this M alpha beta as well. And for let's ignore alpha beta yet, but U and W, one reasonable choice we can make is observe that the rank 1 update we are using combination of QK and HKPK, right, to generate our V here. So therefore, like a reasonable rank 2 update will be simply using the component of V here. So we may just split like V into like Q and HKPK. So in other words, like we can pick U as QK and W as a HKPK. So then we have this is our update here. And again, of course, we want this secant equation is satisfied. And then by inspection, like we can simply pick, let's say, it's a little bit hard to see, but let me see. So if we pick QK transpose PK is alpha here. Oh, okay, yeah. Then this got cancelled, right? Yeah, it's hard to see, but remember that whenever we have transpose multiplied by something, this is a scalar, right? So this part got cancelled. I just have QK here. Now I'm trying to make this guy cancel with this guy. So I have this HK transpose PK transpose. Oh yeah, okay. This is just a number, right? Again, this is just a scalar. So this is a matrix. This is a row vector. This is a column vector. So the multiple is just a scalar. So this scalar can get cancelled with this guy. So therefore, I would just have minus HKPK cancel with this guy, so that's fine. So anyway, finally, we will just pick an update like this. And but again, the next problem we have is that like we would like to have the H inverse, right? We would like to have the inverse Hessian matrix instead of the Hessian matrix for update. So we need to compute H inverse. And so what I want to say is that you can utilize this Sherman-Morrison formula, and this formula is something like that. If you have a matrix A plus a Vacuum matrix composed of like U times V transpose and take the inverse, will be given by this here. And it's not difficult to show that. Basically, it's just show that by verification. You multiply this by the original guy here, and then I can expand this A multiplied by, let's say, A times U B transpose times A multiplied by A inverse got this part, and then like this multiplied by this get this part here. Then after some algebra, like, you will just get this basically is equal to identity. So this formula is easy to verify. Now the problem is that I honestly gave up last year. I didn't look at it again like this year. Instead, I tried to compute like H inverse with this H here, that with this expression here, with also with the Morrison formula. I guess I tried several. I gave up somewhere here. So any guys are interested, I'm still giving a bounty for that, like for the whole course, like to solve this algebra. So let me restate the problem. I supposed to prove this. Eventually should be able to show that PB is equal to this guy here by using this formula, these two formulas. But I simply just got stuck somewhere. So if you guys, I'm sure you guys are better in algebra than I do, because I'm really old now. Like in terms of math ability, I'm almost become retarded now. Like so therefore, like yeah. So if you guys want to get a 3% bonus on your just doing some tedious algebra, just try it out. So anyway, like this will be the final update eventually. And actually, I think that last year I did look into all the references, and all of them they just say by using this what's the name again? Sherman-Morrison formula, you should get this expression. So I guess maybe it's not difficult. I don't know. All of the books just say that, and all of the references just say that. But then when I try it out, I just got stuck. So anyway, so let's just give a summary of this thing here, like the BFGS again. So then the update, therefore, basically, we have the search direction is given by the inverse hashing multiplied by the gradient, and then we will use line search to find the optimum along that direction. And then we have the update. B is given by the formula that I cannot derive in the last slide. And then like you just keep it away until like you are satisfied. When basically the gradient is small enough, then you just quit. And by the way, I did take up line search this year though. Like last year I didn't talk about that. So for line search, for example, we can just use a golden session search. So the idea would be like this. So let's say if you go along that direction, so I just think that there's a minimum there, but I don't know where is it. So then let's say I first look into this, and I look into, let's say, I look into these several points now. Now in the next step, I look into this guy and decide like whether where's the minimum. So let's say if like I inspect this point x4 and I got this, where do you think the minimum? Is the minimum between x2 and x3? Or like let's say x1 and x4? Or let's say like, I don't know, x1 and x7 and x3 will be stable, right? It will be like between x2 and x3 and x1 or x4? So okay. If my minimum is, if not, I should say minimum. If I inspect at this point, I got this, then I'll argue that it's quite likely it's not quite likely. It looks like my minimum should be here, right? Because it looks like if this function is kind of smooth, it looks like it should be something like that, right? My minimum should occur here. On the other hand, if I inspect here, somehow I should suspect that my minimum will be somewhere in this range here, right? So basically, depending on like what's the result here, we can determine whether like next time whether the minimum is in this range or in this range here, and then we can probe further. Of course, like one question is like how do we design like where to probe? So or in this case, why we probe x4 instead of like somewhere else here? So an argument here is that we want to maximize our search average search speed. Then we want to each time just like no matter we kind of like get result here and get result here, we shrink the search range like more or less the same. So therefore we should have a constraint that like x1 to x4 is same distance as like x2 to x3. So we have x4 minus x1 equal to x3 minus x2, or a plus c is equal to b. And and of course, then if I give an x1, x2, and x3, I know where to find x4. But my question is like, how about at the beginning I only know x1 and x2? Like how do I pick? X1 and x3. How do I pick this x2 here? So the golden session search simply use this rationale that I will just assume like for each iteration, the spacing will be like proportional. So in other words, when I probe, in other words, something like C over A should be equal to A over B, something like that. You can think of this is the Oh, okay. I'm not going to say anything. That I'm taking a hold to myself, but is that does it make sense to you? Like it looks reasonable, right? If my spacing for each iteration is proportional, it seems very reasonable that I would like to have this over to this have the same ratio of A to B. And if I do that, then I basically have two equations now. I have A plus C is equal to B, and like C over A is equal to A over B. Then I can just substitute this into here. Then I have this one. Then I have B over A minus 1, and then this I 1 over this. Then I have a quadratic equation here, and I can compute B over A, and that will get me this like 1 plus square root 5 over 2, or like 1.618 something something. And this is known as the golden ratio. So that's why I call it golden section search. So, okay. And a couple more remarks about BFGS. We mentioned BFGS, but we also mentioned at the beginning there's another kind of approach known as DFS. It turns out that DFS is really closely related to BFGS. So remember what we did in the rank 1 update. We say that we don't really need to compute the update for B, knowing that how we update for H, because we have basically we have HP is equal to Q here, that we get some equations, and then we have BQ given BQ equal to P. We can simply change the variables of Q and P, swap the variables of Q and P, then we should get a similar update equation, right? So, and for BFGS, we didn't use this trick. Instead, remember, we used the Sherman-Morrison equation and tried to derive that. Tried, I didn't finish that. And then got that update equation. Now, if we use this instead, then the update formula for BK will have something like this, right? We have a totally different update equations. And it turns out this is exactly what we know as DFP, the other kind of DFP or DFS, other Cauchy-Newton method. But it turns out like typically this approach is kind of worse than BFGS, so therefore it's not as widely used. And some theoretical note, but it's kind of neat, is that like we can interpret this in another way, BFGS and DFP. So remember that like what we have at the beginning, we try to have rank 1 and rank 2 update, and we try to satisfy several equations. We try to satisfy the secant equation, and then we need to make sure that BK and HK is symmetric, positive, definite. And note that for the rank 1 update, because it's rank 1, we have like less degree of freedom, right? We already satisfy both of these conditions here. Now, when we consider the rank 2 updates, we actually have additional kind of degree of freedom, right? So therefore, we should be able to satisfy more conditions. And it turns out that like for BFGS and DFP, you can consider them as simply rank 2 update that satisfy these two equations, these two conditions, and one more conditions. Basically, the other condition is that the weighted Frobenius norm is minimum, where the weighted Frobenius norm of the changes is minimum. So basically saying that like you don't want the update to be too big, right, each time the update steps. So you simply compute the difference between the Frobenius of these two, the two inverse Hessian, and then compute the weighted forbiddance norm, where the weighted forbiddance norm, what it means is simply equal to this guy, and that is basically you weight each of the element in the matrix, and you square them and sum them and take the square root. And it turns out that the difference of BFGS and DFP is just they use different weights, and it's really neat. So like BFGS, you use a weight is equal to H, and DFP is using a weight is equal to H inverse. So I guess I'll just finish with this LBFGS quickly. Let's see, is that long? I guess, yeah, it's pretty short. I guess I'll just, so finally, like let me just briefly go through this LBFGS. As I mentioned at the beginning, that problem of BFGS is that like you need to store the Hessian or the inverse Hessian, right? And that thing depends on the dimension of your problem is n squared, right? So it can be huge. And in practice, like instead of storing that, what we can do is like remember that we have the update tool, right? If you look at the update tool here, and let's say we each time we need to utilize the p-phase B here, so therefore we need to store the p-phase inverse Hessian. But let's say we don't store this, but instead we just assume this to be I identity. Of course, this will be a very bad approximation, right? But what we can do is like instead of just iterate one time, we iterate L times, many times, like L times more precisely. So therefore called LBFGS. And if we do that, then basically you kind of trade off the speed, right? Because each time you need to iterate much more time, and also you trade off the accuracy as well, because now even though you can iterate L times or N times, it's still just an approximation, right? It won't be as exact as the beginning. But you can drastically decrease your storage, right? Because now the only thing you need to store is just this P and Q here. It's just n-dimensional vectors. So the dimension, I mean the in terms of dimension of storage, you kind of decrease by n times basically. So n is the number of parameters. And okay, I guess. Okay, maybe I'll just say one more thing here and then stop. So actually, it's a little bit like what we talk about the last tour of like accelerated gradient. BFGS and LBFGS have similar issue also. Like when you are dealing with mini batch, I mean not utilizing all the training data, or like your training data is like pretty small, then your approximation of your gradient and Hessian become not very accurate, and your optimization results will be not very good as well. And comparing with like even 1D approaches like Adam and so on, this will become even worse. Therefore, so in practice, like this kind of approach is better for smaller problems, or like for problems that you have very precise training data. I mean, in the sense that you have, for example, like we will talk about later on, like for example, some new style transfer, like you have like doing some artificial kind of arts using deep network, like you generated images like that. Then typically you can use your own image as the training set, and that image, because you just use one image as your training set, and that it will be like you don't need to use many data. It's just one piece of training sample or like training image. And in that case, it makes sense to really use this second order approach, and we will do it well. For problem like image-led, that kind of competition, this kind of approach may not work well. Like you may want to stick with like first order like approximation. I mean, like atoms and so on. Okay, I guess I will just stop here and then I will talk about something else next time.